Hello everyone. In this video we'll make a small revision of all the things that we have learned until this point. Then we will solve some exercises together in order to make sure that we understand every concept clearly. So in summary, we have talked about the multiplication principle, which states that if an event can occur in n ways and a second event can occur in k ways independently of the first, then both events can occur in n multiplied by k ways. Then we talked about the n factorial, which is equal to 1 multiplied by 2, and we keep multiplying until we reach number n. N has to be a natural number, and in fact, the n factorial is equal to the amount of permutations of n objects taken n at a time. We also saw that 0 factorial has to be equal to 1. I remind you that permutations are ordered arrangements of objects. After that, we constructed the general formula for the amount of permutations of n objects taken k at a time. That is equal to n factorial divided by n minus k factorial. And finally, we learned the general formula for the amount of combinations of n objects taken k at a time, and that equals n factorial divided by k factorial multiplied by n minus k factorial. In the case of combinations, the order does not matter, and in fact, the permutations are related to the combinations with this formula. The amount of permutations is k factorial times bigger than the amount of combinations. And now it's time to solve some exercises. So here's the first exercise. We all know that the genetic code is triplet, and that means that a sequence of 3 nucleotides codes for an amino acid. The question is why the genetic code is triplet and not, for example, doublet or quadruplet. We know that there are 20 amino acids in nature. And in the DNA, we have 4 different types of nucleotides based on their nucleobase, which can be A, T, G, or C. So we have 4 choices in total. Let's say, for example, that the genetic code would be doublet. Okay, then we would need 2 nucleotides to code for an amino acid. Each of them could be A, T, G, or C, so due to the multiplication principle, we would have 4 to the second power equals 16 codons. Notice that 16 is less than 20, so there would be 4 amino acids that wouldn't match with any codons, thus the code could not be doublet. Since the genetic code is triplet, we have 4 to the third power equals 64 possible codons to code for 20 amino acids. And this is the first case in which we exceed the number 20, which is the total number of amino acids in nature. If the genetic code was quadruplet, we would have 4 to the fourth power equals 256 codons to code for 20 amino acids, which corresponds to a great amount of redundancy. In the next question, we have a double helix of DNA with a size of 20,000 kilobase pairs. Assuming that there are no mutations, how many different helices of this type are there? The answer is pretty straightforward. We have 4 nucleobases and 20 million pairs, so in total we have 4 to the 20 millionth power helices. But the main question is, does the direction of the strands matter? In the problem, we didn't mention the direction of each strand, but we noticed that, for example, 5' A, T, T, G, C, 3', which binds with 3' T, A, C, G, 5', is actually different from 3' A, T, T, G, C, 5', which binds with 5' T, A, C, G, 3'. So someone might think that we have to multiply our result by 2, since there are 2 possibilities of directions. However, this is not true. Let's fix the directions of the helices and take, for example, this sequence. Okay, then by taking all possible combinations, we will have counted unintentionally this sequence as well. Now, if we change the directions in the first double helix, okay, we see that the new helix we get is actually similar to the second one. So if we multiply our result by 2, we double count the helices, which is false. We conclude that the direction of our DNA strands does not matter, and we shall not multiply our result by 2. In the next problem, we have an imaginary plasmid that consists of 5 genes. We want to find the possible orders that these genes can be placed inside the plasmid. Since now we have only talked about linear permutations. This time, instead of linear, we want to find circular permutations. There is a small difference between those two, and we'll see it right away. Let's say, for example, that our genes are A, B, C, D, and E. A possible order of those genes inside the plasmid could be this one. We place A first, and then we put all the other genes clockwise. We notice that if we move every gene to its right, etc., we get the exact same permutation. And in fact, this can be done 4 times, so that the linear permutation ABCDE corresponds to 5 circular permutations. Hence, we can calculate the number of circular permutations by relating them to the linear permutations. Each linear permutation corresponds to 5 circular permutations, so there are only 1/5 as many circular permutations as there are linear permutations. We know that the total amount of permutations of 5 objects taken 5 at a time is equal to 5 factorial. So the final answer to our problem is 1/5 of 5 factorial, and that is equal to 4 factorial number of plasmids. We can now construct the general formula of circular permutations of k objects, and that is equal to k minus 1 factorial. We proceed with the next and the final question, which is to prove that n over k is equal to n over n minus k, and then interpret the essence of this result. So all we have to do is to apply the known formula twice, and we know that n over k is equal to n factorial divided by k factorial multiplied by n minus k factorial, whereas n over n minus k is equal to n factorial divided by n minus k factorial multiplied by n minus parentheses n minus k factorial, and we simplify this to get n factorial divided by n minus k factorial multiplied by k factorial. So we see that these two are equal and the problem is solved. In order to understand why this equation is true, we take, for example, n equals 4 and k equals 3. So we have 4 amino acids and we combine them 3 at a time. Notice that for every triplet of amino acids that we select, there exists an amino acid that is left unselected. So the amount of combinations that we make by selecting amino acids is equal to the amount of combinations of the amino acids that are left unselected. That means that 4 over 3 is actually equal to 4 over 1. So that's it for today. In the next video, we'll talk about a combinatorial problem that is harder than the ones we solved today, and that's why it will have its own video. If you have any questions, feel free to share them in the comment section below, and see you in the next video.